will be talking about calculations involving inverse trigonometric functions, as well as calculations involving inverse trigonometric functions and the right triangle. So there is a relationship there through the regular basic trigonometric functions, which leads to calculating values of angles using the inverse trigonometric functions. So we'll look at that in detail in this section. We will be referencing section 5.5 just to review that content. It will be very useful if you remember that material from section 5.5 in this section. Okay, so to begin with, let's start with the sine of x and inverse sine of x functions. Okay, so from section 5.5, so recall that, so we remember from that section that sine of x has a restricted domain, right? Let me bring this back. So this is the this is a slide from our talk in that section 5.5. So this is the sine of x function, and in order for this function right now as it is, it's not a one-to-one function, but in order to make this a one-to-one function, if you recall, we had to restrict its domain, right, from negative pi over 2 to pi over 2. That way a horizontal line can intersect that segment of this curve at only one point, which means that once we restrict the domain to minus pi over 2 to pi over 2, the sine of x function is a one-to-one function, therefore it has an inverse. So this is from that. And right here, you can see that restricted domain, which was between and equal to negative pi over 2 and pi over 2. So just a quick mention, this is referencing the domain of the sine of function. So when we switch to inverse sine function, the role of the domain and the range are swapped. So this minus pi over 2 to pi over 2 becomes the y-axis. So we'll go from negative pi over 2 to pi over 2 here, from pi over 2 to negative pi over 2 here on the negative side of the y-axis. And on the x-axis, we'll go from negative 1 to 1 for the inverse sine function, not here. But I'm just giving you a heads up what's coming up when we get to the inverse sine function. The domain and range are swapped, and that we know from Math 126, Pre-Calculus 1. Okay, so from that, we remember that, let me add a picture to this discussion. So sine of x has restricted domain, right? Just from the slide that I brought up, and the restricted domain is that argument x should go from negative pi over 2 to pi over 2. We know that. For the function to be one-to-one. Okay, so let's draw a picture. We're going to need that. So here's our x-axis and y-axis. And suppose we have some angle theta, let's say that, something like that. So this is the terminal side of that angle, right? So this is the angle theta. And let's, even we're going to be talking about right triangles quite a bit in this section. So let me just construct a rough right triangle based on this terminal side. So I'll just make it dashed. So let's think of that as a right triangle with a 90-degree angle there. And let's label this side as y. That's along the y-axis. So from here to here, let's call that y, some measure y. Let's call this hypotenuse. Let's give it the letter lowercase r. The other thing I want to add to this is that here we are in quadrant 1. If you think back to the unit circle, right, that would be quadrant 1, and then here we are in quadrant 4, right? Just thinking ahead in terms of what's coming up in our discussion. Okay, so let's write down for sine of theta. Let's write down what would we have to have in order to measure the sine of theta. So sine of theta would be equal to, it's the opposite side divided by the hypotenuse, right, for the sine. Opposite side divided by hypotenuse. So it'll be y over r. Okay, so this particular argument, so that in the sine function, that theta is part of the domain or range. Can you answer that when watching this video? Would that be a domain, part of the domain, or part of the range? It would be part of the domain. So domain, and we said that we're going to restrict that to that. So it was x up there because we had sine of x. Now we're using theta, so I'm going to say theta has to be restricted from negative pi over 2 to pi over 2. In our picture here, that would mean from pi over 2 which is the positive y-axis, to negative pi over 2, which is the negative side of the y-axis. Okay, so, and then that's, I'm thinking ahead with respect to this. Just wait a second, because this theta now is the domain. So the negative pi over 2 is here, and pi over 2 is here for this. But in a second, we will get to the inverse sine function, where the roles of the x, the domain, and range are swapped. So, and this y over r is the range, right? That's the range of this function sine theta. And we know that for the initial basic sine function, that y over r must range between -1 and 1. Okay. All right. So now we're going to swap the domain and range. Why? Because we're going to write down the inverse of sine functions. So I'm going to write down a note here from Pre-Calculus 1, or Math 126. So let's recall from Math 126, or Pre-Calculus 1, that the domain and range swap roles. So the domain and range are swapped or are swapped between a function and its inverse. That's always true for any function, including the trigonometric functions. So what does that mean? So take a look at this. When we write the inverse sine function, then the range over there becomes the domain here, y over r, right? Equals the domain in sine function becomes the range here, theta. Very important to remember when we write down the inverse trigonometric functions. So now this pi is going to be the range, which is between negative pi over 2 and pi over 2, and this y over r, I hope you're looking up and down between these two and comparing their domain and range with each other. And this will be the domain, which is going, so y over r, it's now ranging between -1 and 1. Okay, so that's that. That's why I think I jumped the gun a little bit too early, and this is what I meant to say that range goes from negative pi over 2 to pi over 2. This is what I had in mind. I had the range of the inverse trigonometric function in my mind when I talked about that. So with respect to the sine function, no. With respect to that, you'd have negative pi over 2 here and pi over 2 here. So it'll be along the x-axis because that would be part of the domain there. But it would be part of the range here. I hope that's clear. Okay, so let's look at a few examples of applying this. Suppose we want to find the exact value of each expression. So we're going to have part A, B, C, and so on of each expression below. Okay, so let's go with part A, and we want to evaluate this inverse trigonometric function like that. So that's the question we want to answer. Well, so this question, if you recall that, so whenever you have an inverse trigonometric function on the left, then the other side of the equality is always going to be an angle of something, maybe 30 degrees or pi over 6 or pi over 3 or 60 degrees and so on. So that side is always an angle. So let me we're introducing this topic, so I'm just going to make sure that I'm at least mentioning that once. So this is some angle. So this angle, theta, we are looking for, must be in a range, right? Must be in the range, in this range. So we have theta must be between negative pi over 2 and pi over 2 for the inverse sine function. Okay. So we know that we know that sine of theta equals pi over 3 is equal to square root of 3 over 2, right? We know that from this special table of angles and or trigonometric values. But these are, remember why these are so important? These are important because these are the reference angles. The reference angle is an angle between the x-axis and the terminal side of any angle. So if you have an angle, if a positive angle of 150 degrees, what is the reference angle for that? It is 30 degrees, right, in the second quadrant. So because the terminal side of 150 degrees is within 30 degrees of the x-axis. So that's why these angles are so important. Okay, so but we know that sine of theta is equal to, well, by the way, since we brought this back, so pi over 3 is 60 degrees. Sine of pi over 3 is square root of 3 over 2. Okay, so we know that. But this is not what we have. We have minus square root of 3 over 2. So what would this another angle have to be in order for the sine of that angle to be negative square root of 3 over 2? So we know that. But what we need is sine of theta equals question mark to be equal to minus square root of 3 over 2. So that angle would be the angle we're looking for. Okay. So we must have, because the range of theta is between negative pi over 2 to pi over 2, then this angle cannot be pi over 3 because it's going to be positive, so it has to be minus pi over 3, which means it should be in the fourth quadrant. So the angle should be here, minus pi over 3 in here, in order for the sine to be negative. And let me bring this back, this old graph of the unit circle. So in the fourth quadrant, the sine is negative, which is what we want. So therefore, we will have the theta is equal to minus pi over 3. So that's the answer to that question. So the question mark is equal to minus pi over 3. And remember, that side, whenever you have an inverse trigonometric function on one side, the other side is always an angle of some kind. Okay, so that's that. And note that I want to add right at the very end, note that this angle is between negative pi over 2 and pi over 2. It must be that way. Okay. Okay, so let's do another example. So part B. So we want to evaluate this inverse sine function. So let's remember that this question mark is an angle. Well, let me write it as angle theta. It's a theta that we're looking for, this side. Okay, and this one, this means that because it's part of an inverse sine angle, it means that sine of some angle theta must be equal to -1. That's what it means. Okay. So in that range, in the range for theta, so in the range for theta, which is -π/2 to π/2, and I'm using the interval notation this time, in this range, the only angle theta with sine of theta equal -1, right, would be -π/2. Is negative, pi equals -π/2. So you can write the answer like that, or you can say sine of, or you can say, so let me say, or this, or sine, inverse sine of -1 equals -π/2. Whichever way you prefer is fine. Okay. Let's do another example before we go to the cosine function. So part C, we want to evaluate sine, inverse sine of 1/2, like that. So once again, we know that whenever we have an inverse trigonometric function of any kind, inverse sine, inverse cosine, inverse tangent, cotangent, whatever, the other side is always an angle that we're looking for, theta equals question mark. And this piece, being part of an inverse sine function, means that there must be an angle such that sine of that angle is equal to 1/2. Okay. Now I know some of you are already writing down what theta should be, right? Within the range -π/2 to π/2, what angle would have what angle would have a sine of it that would be equal to 1/2? Well, that would be π/6, right? Some of you already know that, but we can go to this reference, the special table of trigonometric values. So we have the sine of 30 degrees, or π/6, is 1/2. So this one is maybe too easy, right? So let me write this down. In the range, so you have this in your notes, in the range theta equals -π/2 to π/2, we have the only angle theta with sine of theta equals 1/2 is theta equals π/6. Either that, or you can write down inverse sine of 1/2 is equal to π/6. Okay, like that. Okay, so I hope things are beginning to make sense as far as this topic is concerned. Now let's move forward to cosine function and its inverse. Like that. So once again, we want to recall from our discussion of section 5.5. Recall that for cosine of x, restricted domain is theta being between 0 and pi. And I can bring back that slide from our discussion in section 5.5. Right? This is the cosine function. And as you can see in its original form, it has no inverse, so we had to restrict the domain from 0, right there, 0 to pi, which is that point, 0 to pi, which is where that line begins and ends, in order for the cosine function to have an inverse. And so x is between 0 and pi. In our discussion today, we're not using x when we're talking about the inverse function. We're going to be talking about theta, but it's the same thing. Okay, so knowing that, let's draw a picture of this, of course. So 0 to pi, right? So this would be pi, right? This side would be pi, and that would be 0. The angle going from 0 to pi would be going that way, right? Then let's take some line, let's say here, anywhere here. Let's say that's the terminal side of some angle. And so I'm going to put a theta angle here, and then let's turn this into a right triangle, like that. And that's the 90-degree angle. Let's add the quadrant in which the domain is. The domain swings from quadrant 1, which is here, to quadrant 2, which is here, right? The other thing that I'd like to label here is this side, because cosine would be the adjacent, cosine of any angle would be the adjacent side divided by the hypotenuse, and the adjacent is along the x-axis, so I'm going to label it as x. The other one was along the y-axis, so for the sine function, I mean, and we labeled it y, right? For the sine function, we had opposite divided by the hypotenuse. So we said, because this was along the y-axis, we said y over r. That's for sine. For cosine, it's the adjacent divided by the hypotenuse, lowercase r. So we're going to write down sine of theta, cosine of theta is equal to x, or the adjacent side, divided by the hypotenuse, which is r. Okay, let's quickly write down what each of these terms or variables represent. So this would represent the domain of the cosine function, right? The one that is restricted from 0 to pi. So this would be the domain. I mean, the theta is part of the domain. It's not the domain, it's part of it. And so theta is going to go from 0 to pi, as we've been discussing. Now, what about this? What does x over r represent? X over r represents the range, or part of the range, part of the range. And the range would be equal to minus, it goes from minus 1 to 1. So x over r can go from negative 1 to 1. And all of this is for the original cosine function. This is important because in a few seconds we're going to talk about inverse cosine function, in which case these two are swapped. So this range x over r becomes part of the domain and theta becomes part of the range. So let's see how that works. So thus swapping the domain and range, we have to, right? We're moving towards the inverse cosine function. So we have to swap these two. Swapping the domain and range, we have this function, inverse cosine function. So inverse cosine function. So let's see. The range becomes the part of the domain. So x over r. And the domain becomes the range, like that. Okay, so I want to write that down. So this is our range. And theta is going from 0 to pi. And this goes from, as we know, from negative 1 to 1, right? Negative 1 to 1. Okay, so let's see. I think I have everything included. Yep, so let's look at an example or a couple of examples on this. So we want to find exact value of each of the following expressions if it's defined. If it's defined. Why did I add this? Quite frankly, because your book has problems like this, statements like this. So I just wanted you to become or get used to it or become familiar with it in the video. But I guess in your book, there are problems where there is no exact value that can be found because the theta would be probably outside of the range of what we need to have from 0 to 2 pi. That would be one case where you wouldn't have the inverse function defined. But in the examples that I go over, I'd like for them to have a solution. So you won't find cases where it's not defined in the examples that I work on. But if you have questions about it, please stop by my office hours. We can go over that. Okay, so part A. We want to find the exact value of cosine of inverse cosine of negative square root of 3 over 2. Right? So that's what we want to find. Well, so this would be an angle, right? This is what we're looking for is an angle theta. And this here, this minus square root of 3 over 2 means that there must be some angle theta for which cosine of theta is equal to minus square root of 3 over 2. Of course, provided that this angle is between 0 and pi. That's our condition. Okay, so in that range 0 to 2 pi, in the range of theta going from 0 to pi, right? So the only angle theta with cosine of theta equaling minus square root of 3 over 2 would be in which quadrant? Before we write the answer down, think about this. The range, this angle we're looking for must be between 0 and pi. Where can it be? So if I bring this back, can it be here? No, because the cosine of some angle in the first quadrant is going to be positive. We have negative. So in the range between 0 to pi, this cosine, if the answer is negative, the cosine, that angle has to be in the second quadrant, okay, where cosine is negative. So, but from the table of special trigonometric values, for the cosine, look at that, and square root of 3 over 2, right? Positive. That's 30 degrees. So cosine of 30 degrees is square root of 3 over 2. But that's positive because this table is, these angles are our reference angles. So in the second quadrant, we want the reference angle to be, so I'm just going to draw a quick small figure here, a little sketch. So we know in this 0 to pi range, we need to be, and I'm going to roughly sketch a circle here. We know we need to be here. We need to be in the second quadrant. There's only two quadrants where we can be, either quadrant 1 or quadrant 2. We need to be in quadrant 2 because this quantity is negative, and the special angle that we just saw, it was 30 degrees. So that's the reference angle. So 30 degrees is that angle. 30 degrees is pi over 6, right? So what is that angle whose cosine? It's going to be in the second quadrant with a negative result, equaling negative square root of 3 over 2. So we know the reference angle must be pi over 6, right? Because of these values. These are reference angles, and so square root of 3 over 2, but that's positive. So whatever that value, we can figure out by subtracting pi over 6 from pi. So theta would be pi minus pi over 6, and of course this is equal to 5 pi over 6. Like that. So that angle is between 0 and pi, and is the result for this inverse cosine equation. So you can either leave the answer like that, or you can write inverse cosine of negative square root of 3 over 2 is equal to 5 pi over 6. Either way, it's fine. So just remember, please, that this table of special trigonometric values gives us the reference angles. These reference angles are very, very important in trigonometry. Okay. So let's do another example. Suppose now we want to calculate this value, inverse cosine of negative square root of 2 over 2 equaling that. So we want to find the value for the question mark. This is my favorite because the angle, you know, the reference angle I should say, you know it's going to be pi over 4. It's my favorite because look at the special trigonometric values for 45 degrees, right, for this one. The sine is equal to square root of 2 over 2. The cosine is equal to square root of 2 over 2. It's the same thing, right? 45-degree angle. Then the tangent and cotangent are 1 and 1, and the secant and cosecant are square root of 2 and square root of 2. Very easy numbers to remember for the 45-degree angle. Okay, like that. So we know that we're looking for some angle, theta, and we know that that is in combination with the inverse cosine means that there must be an angle theta that we're looking for such that cosine of that angle is equal to negative square root of 2 over 2. And we know for the cosine function, the range of theta must be 0 to pi, right? So 0 must be, we must find theta such that it's between 0 and pi. So let's write this down. So you don't have to be, say on an exam, you don't have to be this detailed when you write down your answer, but I'm writing it down so you know the reasoning behind each answer. So in the range of theta equaling bracket 0 to pi, close bracket, so the only angle theta for which we can have cosine of theta equals minus square root of 2 over 2 is in quadrant 2, right? Because in the first quadrant, everything is positive. Everything is positive. Going from 0 to pi, everything in the first quadrant is positive, and we have minus square root of 2 over 2. So we must be in the second quadrant minus because of that minus. And the angle of reference, or the reference angle, let me correct myself there, reference angle should be, move this on, cosine of 45 degrees is square root of 2 over 2. So our reference angle in the second quadrant is 45-degree angle. So is in, let's see, is in quadrant 2. That's what I wanted to write down. Is in quadrant 2. With the reference angle theta r, let's say, equaling pi over 4. Okay, so what does that mean? Why do we care that what is the reference angle? Well, let me once again, like before, draw a quick picture here. So let's call it theta, if we're calling it theta. Let's call it, instead of x, I'm calling it theta. Maybe I should fix the other one too. So this one, instead of x, because I've been using theta in this example, I want to change that to theta, not x anymore. Okay. We used x up here, so we have x there, but here we're using theta. So that should be theta. Okay, theta going from 0 to pi, and I'm going to draw a rough sketch of the unit circle. We know we're going to be in the second quadrant, right? We know from this we're going to be somewhere here. Well, not somewhere, because we know the reference angle, right? The reference angle is right there. That is theta r equals pi over 4, which is the angle between the x-axis and the terminal side of this angle. So what was the the actual angle? The actual angle must have been from all the way from here to here. So this is the angle that we're looking for. That angle is the question mark you see there. We're looking for that. Well, we know the reference angle, which is a huge help, because all we have to do is say, oh, that angle must be equal to pi minus this piece, pi over 4. So theta is equal to pi minus the reference angle, and this will be, of course, 3 pi over 4. You can either write the answer like that, or you can say that inverse cosine of minus square root of 2 over 2 is equal to 3 pi over 4. Either way, either that or this one. Okay. So let's see another example of this kind before we move to the tangent of x and inverse tangent of x. Question mark. So I think by now you're on a roll. You already know what I'm going to do here, right? I'm going to put a dash circle around it, and I'm going to say that we're looking for an angle here. That's theta that we're looking for, and this piece, because it's part of an inverse cosine function, means that there must be some angle theta for which cosine of theta is equal to 1 over 2. Okay, so once again, the angle theta, the range, is restricted between 0 and pi. And this value is restricted between -1 and 1. Okay, so let's write that down, that in the range of theta equaling 0 to pi, so the only angle theta for which cosine of theta is equal to 1/2. Do you remember what angle this is? What reference angle is that for which cosine of that angle is 1 over 2? Do you remember that? Well, if you don't remember, here's the special table of special trigonometric values. So cosine 1/2 that is pi over 3, or 60 degrees. Cosine of 60 degrees, or pi over 3, is 1/2. This column is all for cosine of the reference angles, right here. So for which cosine of theta is that, is in, let's see, is in quadrant, well, which quadrant that is? Let's see. That's pi over 3, but that's positive 1/2, right? So we're going from 0 to pi. That's the range of restricted range for inverse cosine function, from 0 to pi. So we either have to be in quadrant 1 or quadrant 2. Can we be in quadrant 2? No, it's negative. Cosine of angles in the second quadrant is going to be negative, not positive. We're positive. So we are in the first quadrant where the cosine of any angle is positive. And from this table of special trigonometric values, we now know that that's a pi over 3, or 60 degree angle, cosine of which is 1/2. For which that is in quadrant 1. With reference angle theta r equaling pi over, what was it? Pi over 3. Okay, so you can then, therefore, so we can say, therefore, the answer to that question is theta is equal to pi over 3, or inverse cosine of 1/2 is equal to pi over 3. One trivial thing that I haven't mentioned yet is that in the first quadrant, right here, in the first quadrant, reference angles are equal to the actual angles that we have. So that's the thing. In the other quadrants, no, that's not the case. But in the first quadrant, the reference angles are equal to the actual angles that we're calculating. So in this case, this is clearly in the first quadrant because that's from 0 to pi, the only quadrant where the cosines are positive is in the first quadrant. So we know that. So we know the reference angle is going to be the actual angle we're looking for. Okay, so I thought I mentioned that as we go through these things. Okay, so let's move now to the tangent function and its inverse. Okay, so recall, this is again going back to that. I'll bring the slide back again, but recall that the tangent of x function with restricted domain, and I'll bring that back now. So here we have, this is the slide from our discussion from section 5.5. This is the tangent function. So if we wanted it to have an inverse, then we had to restrict the domain to to go from negative pi over 2 to pi over 2, right? Notice this is not like the sine function where you have x equal to greater than negative pi over 2 and equal to or less than pi over 2. This is greater than negative pi over 2 and less than pi over 2. That's because tangent is sine divided by cosine, and cosine function at those endpoints is going to be 0, and we don't want to divide by 0. That's why the minus pi over 2 and pi over 2 are excluded from the domain of the tangent of x function, the restricted domain, that is. So it has restricted domain, theta being greater than negative pi over 2 and less than positive pi over 2, right? So let's draw a picture. So the x-axis, notice how I'll draw the picture for this one. The or the pi axis, now for us the domain now, for this tangent function, the domain is part of, theta is part of the domain, and when we get to the inverse tangent function, theta is going to be the range, right? But for now, it's part of the domain. So theta, that is going to range from not including negative pi over 2 and pi over 2. So I'm not going to draw the vertical axis or the y-axis solid. It's going to have to be dashed. So like that. Like this. Well, okay, so this is y. Again, I'm thinking ahead here to the inverse. I'm thinking about the range of the inverse tangent function, but now we're talking about the tangent function. So when we get to the inverse, this graph will make a little bit more sense. So let me write down here. So if we have an angle like this, and let's call that theta. And I'm going to make this into a right triangle, 90 degrees here. And let me label this as y and this side as x and this vertical side as y on the right triangle. So from here to here is x, and this is y. And then we can write tangent of theta is equal to the opposite divided by the adjacent. So y over x. Okay, right now the range is not theta. The range is y over x. So let's make that clear. So here we have theta that is part of the domain. And remember, for tangent function to have an inverse, we need to restrict the domain to this theta greater than negative pi over 2 and less than pi over 2, positive pi over 2. And then this is our range in the tangent function. And y over x, of course, goes from negative infinity to positive infinity, right? If you have questions about that, let me bring this picture back from our section 5.5. So the range of the tangent function is from negative infinity to positive infinity. Just look at the behavior of that line with respect to the y-axis. So range is going from negative infinity to positive infinity. Okay, and the domain is restricted from negative pi over 2 to pi over 2 with those vertical asymptotes shown as dashed because we cannot cross that. Okay. So now all of this discussion was important. Why? Because now that we're going to write down the inverse tangent of tangent function, this is going to be swapped. So the range becomes the argument and the domain becomes the range for the inverse tangent function. Okay, so let's do that. So thus, so swapping the domain and range, we have, so what happens? What happens is inverse tangent. Now, what do you think I'm going to write here? And what do you think I'm going to write on this side? So range is going to be the domain. So y over x, and the range is going to be the old domain here. So this is going to be theta. All right, so we have everything is swapped, right, between the original function and the inverse function. So now theta is going to be, it's going to range from that between negative pi over 2 and positive pi over 2. And this domain, so this is the range for the inverse tangent function, and this is the domain for the inverse tangent function, negative infinity to positive infinity. Okay, so with that, now this graph would make sense. See, if you look at this range for the inverse tangent function, it goes from negative pi over 2 to pi over 2. And then that's why these lines would have to be dashed if we draw it here. But I should have drawn this picture here because pi over 2 would be up here, negative pi over 2 would be here, and of course theta could not. So once again, pi over 2 would be up here, negative pi over 2 would be this end, and theta could not attain those two values. So therefore, it would make sense if we draw the line dashed. Okay, so maybe this picture would have been better if I drew it here, down here, maybe, like that. Okay. Okay, so let's look at a few examples of applying the, finding the inverse tangent values. So here we want to find the if it is defined. So let's do part A, and we want to find the inverse tangent of negative square root of 3 equal a question mark, right? You already know what I'm going to do. I'm going to draw a dashed circle over this and say, hey guys, that's a theta, that's an angle we're looking for on the other side. Whenever we have an inverse trigonometric function on one side, the other side is an angle measure. And then whatever we have in here, it means that there must be some theta, which we're looking for which tangent of that theta is equal to negative square root of 3. Okay, so we know that theta is must range between negative pi over 2 and pi over 2, right? Keep that in mind as we're looking for this theta. So in the range for theta equals, not bracket, parentheses for sure. So let me make sure that that is in fact a parentheses. So this is parenthesis, not bracket. In that range of negative pi over 2 comma pi over 2 parenthesis, the only angle with tangent of theta equals minus square root of 3, right? That's what we're looking for. We're looking for an angle for which tangent is negative square root of 3. We know that. We're looking for the angle that this is the result of that. So you probably memorized these already, but let's bring back the table of special trigonometric values. So the tangent values which are here, these are the reference angles, right? So the tangent of these reference angles is for 60 degrees is square root of 3. How can you get this? How can you calculate this? Very easily. Tangent is equal to sine, tangent of any value, of any angle is equal to the sine of that angle divided by the cosine of that angle. Sine divided by cosine. So if you don't remember this, but if you remember the sine and cosine for 60 degrees or pi over 3, you can divide sine by cosine and you'll get that. So pi over 3. That's the reference angle. But in the quadrant, so we're for the inverse tangent, we just said that we are allowed to go from negative pi over 2 to pi over 2, excluding negative pi over 2 and pi over 2 and negative pi over 2, right? We're allowed to swing between quadrant 1 and 4. We can be either in quadrant 1 or quadrant 4. But which one? Can we be up here? Definitely not, because the tangent of angles in the first quadrant is positive. We're not positive. We have negative square root of 3. So we're looking for an angle for which the tangent of that angle is negative square root of 3. So we definitely have to be here in the fourth quadrant where the tangent is negative. So, but we still can use this special table of trigonometric values to find the reference angle. Whatever angle we're looking for that, the reference angle is pi over 3. Well, in that case, let's see. So that is with the only angle theta with this result is in this range is theta equals minus pi over 3. Okay, so this is the same as the reference angle. So I just wrote it quickly. Or you can lead to it by saying that, so the reference angle, so theta reference is pi over 3, because the reference angle is always positive. But because we know we are in quadrant 4. So let me add that. Is in quadrant 4. Okay, and that's so the reference angle is pi over 3, but because we know we're in quadrant 4, so it'll be minus pi over 3. Okay, so let's do another example. So we want to find the inverse tangent of square root of 3 over 3 equals the question mark. Of course, because this is inverse tangent, that means this question mark has to be an angle, and this means that quantity, so we must have a theta, for which if we take the tangent of that angle, we get this result. So that means tangent of theta must be equal to this result, like that. Okay, we know that. So remember, and we're going between, this theta is ranging between negative pi over 2 and positive pi over 2. So let's write down again. So in that range where theta is allowed to vary, so in the range for theta equals parenthesis negative pi over 2 comma pi over 2, so notice this is positive, right? And we know that we can either be, for the inverse tangent, we can either be in the first quadrant or the fourth quadrant. So the tangent in the fourth quadrant is negative, right? It's negative, so we know we cannot be in the fourth quadrant. We know we're going to be in the first quadrant. And the nice thing about the first quadrant is the reference angles are equal to the angles we're looking for, only in first quadrant, not in any of the other quadrants. So the only, let's see which one we were working. So the only angle is in quadrant 1, right? Quadrant 1. So in that quadrant, the reference angle is equal to the angle we're looking for. And here, back to our special trigonometric values table, we're looking for, so the tangent equaling positive square root of 3 over 3. What angle is that? It's pi over 6. We're in quadrant 1, so the reference angle is equal to the angle we're looking for. So theta must be, that, or that question mark must be pi over 6. Like that. Okay, let's do another example. Suppose we want to find inverse tangent of 0, question mark. Well, on the left we have the inverse tangent. On the right, whatever we have must be a theta, and we know theta for tangent ranges between negative pi over 2 and pi over 2. Okay, and we know that this one means that there must be an angle theta for which the tangent must be equal to 0. So the tangent of that angle should be 0. So in this range, in the range theta equals minus pi over 2 and pi over 2. So this is these two are the same thing. I'm sure you know that, but just in case, this is the interval notation, and this is just between, it's giving it in a different way. It's the same interval, showing it in an inequality format. Okay, so the only angle theta for which tangent of theta equals 0 is, well, tangent of theta, please remember, tangent of theta is equal to sine of theta divided by cosine of theta, right? So wherever the sine of theta is equal to 0, then the tangent is going to be 0, because 0 divided by anything is 0. So in the range negative pi over 2 to pi over 2, what angle would have a sine of 0? 0. It's 0 angle. Okay, so this would be, so that would be, is along the positive x-axis. In other words, theta equals 0. Or you can either give the answer like that, or inverse tangent of 0 equals 0. Like that. Okay, so this was a good discussion covering how we evaluate inverse trigonometric values. In the beginning, I mentioned that another topic that we're going to talk about is the calculations involving inverse trigonometric functions and the right triangle, right? So we're going to talk about that now. So solving for angles in right triangles. Okay, so let's begin. So in the figure shown, so I have to give a figure here in a minute. In the figure shown, we want to find theta, the value of theta. Okay, so let's see what that figure is. And so we have that. The information given to us is as follows. This side has length 6. The hypotenuse is 10, and we are looking for this angle. Okay. Well, we know that in this figure, given these two sides, if we take the sine of this angle, we will have the opposite side divided by the hypotenuse, right? But that's going to give us the sine of theta, not the theta, right? The sine, so let me write this down. So we know that sine of theta is equal to 6/10, right? The opposite over the hypotenuse. But this is not the answer to our question. Or 2/5, or 3/5, right? We can simplify that. It makes no difference. But for now, let's keep it that way. 6/10, but that's not the angle we're looking for. To find the angle, we need to find the inverse of this. So how does that work? Well, the examples that we just solved said that if you want to find the angle, you need to take the inverse of this sine. So inverse sine of this result. It's going to give us the angle. Okay, so now we have to use the calculator because this number we're not going to be able to find in the special trigonometric values table. So using a calculator, we have theta as 36.87 degrees. Okay, like that. Okay, so, and you can set, I've set my calculator setting to give results in degrees. You can set the calculator to give you radian. I'm not sure if I know how to do. Let me bring my calculator here. So do I know how to go from degree to... In this calculator, I don't believe you can use a calculator, but let's see. So if we wanted to change this to radian mode, let's see. So we can do a quick search. Let me switch to the computer here in a second. So we will, and that way. So this is one way of finding information. I will switch to the computer in a second. So we want to, let me go from that to the computer. It's logging in. So I haven't been using this in radian mode, so let's figure out how we can achieve that. Oh, there it is. So actually I want to switch back to the dock camera so you can see what I did. Okay, so all I did on this Texas Instrument calculator, what I want to do is I gave you this angle in degrees, so I want to show you how you can convert this to radians. That's all. So sine of, so in my calculator, notice that DRG, I hit that, and right now it's set on degrees. So I want to move to RAD or radians, and I'm going to hit the enter key. So now I can calculate this result in radians. I just want to show you at least maybe once, maybe twice, so you know how to go back and forth between degrees and radians, at least using this calculator. But you can do this on any scientific calculator, but maybe on your calculator it'll be a different procedure to get there. Okay, so now that we've switched to radians, let's find out what that inverse sine function is in radians, or this degree in radians. So I'm going to use the inverse sine in my calculator is in the upper function, so I have to say that inverse sine of 6/10, close parentheses, and hit the enter key, and that is the value in radians, 0.64, and I'm going to round the 3 to 4, so points roughly, so or 0.644 radians, or theta equals 0.644 radians. I'll do this on the next example, so you at least you see a couple of examples of converting using your calculator to go between degrees and radians. Okay, so let us do another example here. In the figure shown, once again we want to find theta. So here's the figure. Like that. And then there's the base that is perpendicular to this side, like that. And then let's connect those 2 points. Like this. So this would be theta, 8, 9, and then 90-degree angle. Okay, so we are given, notice the size we're given. We're given the hypotenuse. Let me write that down. So this is the hypotenuse. And this is the adjacent angle, not opposite, right? So here, in the previous example, this was the opposite to theta, right? And this was the hypotenuse. In this example, we are given the hypotenuse and the adjacent side to this angle. So that calls for the cosine function, because cosine function is the adjacent side divided by the hypotenuse. So let's write that down. Just because of these numbers that I have, I'm going to use cosine and no other trigonometric functions. So cosine of theta, we know, is equal to 8 divided by 9 on this, in this case, right? So 8 divided by 9. So we want to find the angle. So this isn't going to help us. But guess what? We can use this to find the inverse cosine of what this information we have, and we're going to find the angle we're looking for, right? So theta, based on this, we have theta equals inverse cosine of this ratio. So once again, using a calculator, we have theta equals 27.27 degrees, or let's calculate this in radian. So let me show you again one more time. So if you, on this Texas Instrument calculator, if you hit the DRG button, it'll give you the option to go from degrees to calculate an angle in degrees or radian. Mine was in degrees, now it's on radians. So I'm okay with that. And now we want to, I can either put this in and hit radian. Well, no, it wouldn't convert that to radians. So let me do an inverse cosine of 8/9, and it should give us this result in radians. So let's do that. So you probably can't see it in the video because it's too small and faded, but right above my cosine function, there is an inverse cosine. To activate it, I'll have to enter that blue button, and then like that. And then 8/9 divided by 9, and hit enter, and I get 0.7588 and so on, right? So I'm going to round this to 3 decimal places, and I'm going to round the 5 to 6 radians. So it will be 0.476 radians. Okay? Or like that. Radians. All right. So let's do one more example. We want to find theta, and here's the figure. So we have some base like this, and then we have a side like this. And then I want to draw this. So this should be a right triangle for this to work, right? So this is our right triangle. So in this figure, all right, so what do we have in this case? We have the angle theta. We are given the opposite and the adjacent angles. We do not have the length of the hypotenuse, right? But we don't care about that because there is a trigonometric function we can use that doesn't rely on the hypotenuse, at least not directly. So tangent of theta will be opposite divided by the adjacent. So this is the 7 is the opposite side we are given, and 18 is the adjacent side. So because of the quantities we have been given, let's use the tangent of theta, which would be opposite, or 7 divided by 18. Okay, now this isn't going to help us right away because we're looking for the theta, not the tangent of theta. But since we have the tangent of theta figured out from this picture, so now we can use the inverse tangent. So we can say inverse tangent of 7/18 equals theta. Okay, so once again, using a calculator, let's take the inverse tangent. Well, I have that number, but I'll use then that to convert it to radians. So using a calculator, the way you would do this, you would, let me show you how you get there. Okay, so once again, using this blue button and inverse tangent, and then I'll divide 7 by 18. So it's going to give me radians, so 0.371 radians, rounding it to 3 decimal places. All right, and I have the result in degrees. So theta is equal to 21.25 degrees. Radians. Okay. So let's see what else we have here. So other examples. Let's do other examples. So in the following examples, this is what we want to do. So here's we have this example, part A. I don't think I can fit this solution because I want to list every step. So let me move to the next page. So next, please see next page. This is little space for me to show everything here. Like that. So this is an inverse sine function within a tangent function, right? Now we know what every inverse trigonometric function represents, right? What does this represent? Well, if you said it represents an angle, you're absolutely right. So this represents an angle, okay? So we can write that down. We can say, let theta be that inverse sine of 3/5. Okay. So given that, thus there must be an angle theta such that sine of theta is equal to 3 over 5, right? Just taking it piece by piece, we know that any inverse of a trigonometric functions represents an angle. So we let that be the case, theta is equal to all of that. Then we know that there must be some theta such that if you take the sine of that theta, you end up with 3 over 5. And that's what I wrote down. But we just talked about right triangles, right? And how to use them to calculate trigonometric and inverse trigonometric functions. So let's write down the right triangle interpretation of this. So let me write that down. This is important, so I'm going to write it in red ink. It's very important, actually. So the right angle I should say the right triangle, sorry. The right triangle, let me correct this, the right triangle interpretation of that is this figure. So we have that. Right? Sine of theta, so this being the theta, it means the opposite side divided by the hypotenuse. So the opposite side must have been 3. This is the opposite side. And this is the hypotenuse. The opposite divided by the hypotenuse. So this triangle you see is the right triangle interpretation of this equation. Very, very important. There is a connection, and I want you to make sure that you're comfortable with seeing this connection. Okay? So now that we have that, then this, let's see, then this we can write that equation, original equation. Since the sine of theta is equal to that, we started with the inverse sine function. We converted this inverse sine function to a regular sine function. We wrote down the geometric or right triangle interpretation of that equation. Now we can find the tangent of this theta, right? Because this theta is the same theta. So instead of that, now we have a geometric interpretation of this. This right triangle is the geometric interpretation of what we have up here. So now we can find the tangent of theta by using the sides we have. And by the way, let's call this point A and this point B. Okay, so I'm going to write down tangent of theta given this geometric interpretation. We're going to write down an equation for tangent of theta. Okay, so this inverse sine quantity, we let that be theta. We know it's some angle. So we let that angle to be theta. Then we wrote, for using this, we wrote the sine of theta equals 3 over 5. We use this regular sine function to draw a geometric interpretation of all of this. Now we can easily calculate tangent of theta, right? Let's write it down. So, according to this, let me write that down. According to the figure above, we can write tangent of theta is equal to, tangent is equal to the opposite divided by the adjacent, right? And this is the adjacent. So tangent of theta is equal to the opposite divided by the adjacent. So 3 divided by the adjacent, which is AB. Write that like that, right? But what is, this is a right triangle. What is AB? We have 2 sides. Can we not calculate the adjacent side? Of course we can, using the Pythagorean theorem, right? We learned all of that from elementary geometry. So using the Pythagorean theorem, we know that tangent, we know what AB is equal to, right? So AB, that's the base here, is equal to square root of the hypotenuse squared minus this side squared. So therefore, we can now substitute in this previous equation with this value for AB. So we have tangent of theta equals 3 over this quantity and 25, that would be square root of 16, right? And that is the tangent of theta but tangent of theta is equal to 3 over 4. Like that. Okay, you can either write the answer like this, or you can say, or you can reference the original and say tangent of, let me move this up, tangent of inverse sine of 3/5 equals 3 over 4. Either way is fine, like that. Okay. Okay, so let's do another example. We want to calculate this quantity, secant of inverse sine of 12 over 13, and that's the question mark. So at this, you've already seen a similar example. So if I were you, I would pause the video and on a piece of scratch paper, write down your own solution for this. And when you're done, come back to the video and see how your solution matches this. It doesn't matter if you think your solution is going to be wrong. Hopefully it's correct, but it doesn't matter if it's going to be wrong. What's important that you generate your own thinking, your own solutions before you see somebody else's solution. That's very, very important in the learning process. Okay, so I trust that you've done that. You have your own solution and now you're back. So we know that any inverse trigonometric function represents an angle theta, right? So let theta be that quantity. We know it's going to be some angle, so we're going to call it theta. Like that. So now, so the only angle for which this is true the only such angle I should say there is, let me change this. So I want to shorten my sentence. So thus there is only one angle, there is only one angle theta such that that is true, such that the above relation is true, and that is, I wanted to shorten my sentence, but apparently it wasn't successful. I still wrote the whole thing. So the only such angle would be sine of that angle theta should be equal to 12 over 13, right? Based on this transition, here, we can write this sine equation. So we went from this inverse sine function to this sine function, but there is a geometric interpretation of this, right? So that is as follows. Let's draw that. So if that's the theta, then sine of theta is really the opposite divided by the hypotenuse, right? So the opposite must be 12, and the hypotenuse length must have been 13. Okay, so we geometrically interpreted this equation. That's all we did. And this is the opposite, and this is the hypotenuse. Okay. So now, based on this configuration, let's write secant of theta. Let's find secant of theta. We know where theta is in relation to these two sides. So let's find secant of theta. So given the above, so according to this figure, we can write secant of theta is equal to, do you remember what a secant of theta is equal to in relation to other trigonometric functions? Well, if you said it's the reciprocal of the cosine function, you're absolutely correct, right? But what is cosine function? The cosine function, and let me use one of my thick markers to label this. So let's call this point A, and let's call this B. So the cosine secant is the reciprocal of the cosine function, and the cosine function is the adjacent side divided by the hypotenuse. Remember that? The adjacent side, or AB, divided by the hypotenuse. So let's write that down. One over the adjacent, which is AB, divided by the hypotenuse, or 13. So let's simplify this, because right now we have a complex fraction. I'll try to keep this figure on the screen as much as I can. So this will be 13. After simplifying that, we get 13 over AB. But AB is unknown at this point, but it doesn't matter because using the Pythagorean theorem, we can solve for it, right? Because we have the other two sides. Using the Pythagorean theorem, we can figure out the length of the missing side in a right triangle. So using the Pythagorean theorem, we have divided by, now we need to figure out AB using the Pythagorean theorem, so let's do that. That is equal to 13 squared minus 12 squared, right? 13 squared, or the length of the hypotenuse squared, minus the length of the opposite side squared. Take the square root of that difference, which is what we did here. Then we have secant of theta equals 13 over square root of 169 minus 144. And let's come up here because I'm out of room here. Like that. And then we have secant of theta equals 13 divided by square root of 25. Secant of theta equals 13 over 5. So you can either leave your answer like that, or if you prefer, you can just write down the original equation that we have. Secant of inverse sine function 12 over 13 is equal to 13 over 5. Like that. Okay, let's do another example. So we want to calculate cosecant of inverse cosine 7 over 25. We want to calculate that. So that quantity, any inverse trigonometric function, represents an angle. Let's call that angle theta, right? So let theta be that, all of that, cosine, inverse cosine of 7 over 25. So therefore, or thus, we have an angle theta such that cosine of theta would be equal to 7 over 25. Is equal to 7 over 25. Okay. Okay, so we know that this must be the adjacent and this must be the hypotenuse, right? So right from the get-go, we know that has to be adjacent side to this angle, and this must be the hypotenuse length. So the right triangle interpretation of this let me say, instead of this, let me say the above equation. Is as follows. Let's draw that. I'm going to label these. So this point A and this point B, we know that theta, let me move this up a little bit. And so theta should be that. This is adjacent divided by hypotenuse for the cosine. So adjacent is that side, 7. Or let me switch to blue ink here, 7. And this is 25, right? Okay. So now that we have figured out this right triangle interpretation of all of this, let's calculate cosecant of theta in this triangle. Okay, so cosecant of theta is equal to, do you know which other basic trigonometric function this is related to? Do you remember that? Cosecant and sine functions are reciprocals of each other. So cosecant of theta is going to be equal to 1 over sine of theta. So then the cosecant of theta from this right triangle, sine would be the opposite divided by the hypotenuse, right? This is the opposite side. But we don't have that. So I'm going to write 1 divided by, instead of sine theta, I'm going to write AB divided by the hypotenuse, which is 25, right? Okay, so we have cosecant of theta equals 20, simplifying this complex fraction, we have 25 over AB, and cosecant theta would be equal to, well, by the Pythagorean theorem, so let me not forget to write that down, by the Pythagorean theorem, we know that AB is equal to, let me bring this down a little bit, AB would be equal to 25, a square root of 25 squared minus 7 squared. So let's write that down. Square root of 25 squared minus 7 squared. Right, so I'm going to use this to substitute for AB in the above equation. So we have 25 divided by square root of 25 squared minus 7 squared. Okay, so we're going to, after this, it's just a matter of simplifying this, right? Cosecant of theta is equal to 25 divided by square root of 625 minus 49. Cosecant of theta is equal to 25 divided by square root of 576, and so simplifying this a little more, we have cosecant of theta is equal to 25 divided by 24. So this is the result, or we can write, if you prefer, cosecant of inverse cosine of 7 over 25 is equal to 25 over 24, like that. Okay, so let's do a couple of more examples. So in these examples, the two examples we have left, right? In these examples, we were given numerical values for all these sides, for these two, and then we could calculate that one. But in the upcoming two examples, we're going to give the answer not in terms of a number like this. So we're going to have expressions like this. We're going to have to calculate expressions like this. But we're not going to give the final answers in terms of a number. We're going to give the final answer in terms of variable x. Again, your book talks about this, so I'm going to talk about it. It's a very useful practice, and for those of you who will move on to multivariate calculus, that would be calculus 3, all of this will be very valuable to remember. All of this trigonometry is going to be very valuable, especially if you're in a civil engineering program, especially for those of you who will become structural engineers and so on. Classes like concrete design, classes like static, dynamic, those classes make extensive use of trigonometry. Okay, so let's do that. So in this example, or in this next two examples, we want to rewrite as an algebraic expression in x. Okay, so that's our objective. So here's one example. Okay, so notice that this is not a number anymore, but we want to calculate this expression, find out what this expression is in terms of x. Okay, so we already know that any inverse trigonometric function is equivalent to an angle or represents an angle. So let us use just like before. So let theta be inverse tangent of x. Okay. So once we do that, then the result is the following. So there's an angle theta such that tangent of theta is equal to x, right? X. Okay, there's x, and then so but this also means the following. So tangent of theta is equal to x over 1, right? So in any other place, if I did this, this would be very silly to do this, to write tangent of theta equals x as tangent of theta equals x over 1. We as you know, we're not going to, if the denominator is 1, we're not going to write it. But in this case, it's a very beneficial thing. It's a very good thing to do. In any other context, like I say, it would be a very silly thing to do. But here, it's a very useful thing to do. So let's see why. So we're going to write down, like before, a right triangle interpretation of what you see here, right? Because going from here to here might be silly, but it's not inaccurate, right? This is still accurate statement. But normally, in mathematics, we don't do that. But let's see why we did it in this case. So we're going to draw a right triangle . So we know that that is a right triangle. And let's take this as theta. So a tangent is equal to, this is from way back in the previous videos, the tangent of an angle is equal to the opposite divided by the adjacent, right? So this is the opposite, and this is the adjacent. So now look at this formula and see where you would put everything. Now is where the 1 comes in very useful in this case. So the opposite of this would be this over the adjacent, which is this one. So the length of this would be 1. So that is x, that is 1, okay, according to that result. Okay, so now let's calculate that original x. Now that we have our geometry or our right triangle figured out, this right triangle is connected to the original function. So we have cosine of theta, right? We took this whole argument as theta, so cosine of theta. Now we can calculate this given this right triangle. Now, cosine of theta, as you know, is connected to the adjacent side, is a ratio of the adjacent divided by the hypotenuse, right? So this being the hypotenuse here. Okay, so I'm going to call it AB. So we have the 1 over AB, right? The adjacent 1 over the hypotenuse AB. So we don't know AB by the Pythagorean theorem. We can easily figure it out, right? AB would be equal to square root of x squared plus 1 squared, or 1. So by the Pythagorean theorem, AB would be equal to square root of x squared plus 1 squared. That's just looking at, because AB is the hypotenuse, right? So x squared plus 1 squared. Now let's substitute this in, which is 1 squared is 1, right? So let's substitute this here. So we have cosine of theta is equal to 1 over x squared plus 1. Okay, let's do another example of the same kind. So we want to calculate this expression in terms of x. So you now know what I'm going to do next, right? So we know that any inverse trigonometric function represents an angle, so let's call that theta. Like that. So we must have, if this is true, then we must have an angle theta for which sine of theta would be equal to x. Okay. So this means let's rewrite this. Sine of theta equals x over 1. On the previous example, you may have thought that it was very silly when I wrote it like that, right, in the previous example, but now you see where I'm going with this. So there's a good reason for that. So we know that this x here is the opposite of that angle, and this 1 must be the hypotenuse of that triangle that we are going to draw in a second. So So the right triangle interpretation of the above equation is as follows. So we have, let's take this as the theta, and opposite would be that, so that's x, right? That's opposite. Sine of theta equals x over 1, 1 being the hypotenuse. And the missing side, the side for which we have no length, let's call that AB, like that. Okay. All right, so now we have our geometric interpretation of the original question. Now all we have to do is find the tangent of theta in this right triangle, or using this right triangle. So we have, given the above figure, we have tangent of theta. Tangent, remember what that represents in terms of a right triangle? It is the opposite side divided by the adjacent side, right? X divided by AB. Like that. So if you want, I can add that here. This would be, with respect to the theta, this would be opposite. And this length is the adjacent side, right? Adjacent to this angle. So tangent of theta is equal to the opposite divided by the adjacent. Okay, as you can see, we don't have AB, but that's no problem because we can calculate it in terms of x from these two quantities on the other side. So by the Pythagorean theorem, so AB, right, AB is equal to square root of 1 squared minus x squared. So let's write that down. Square root of 1 squared minus x squared. Like that. Okay. Let's substitute this in this equation, and we will be done. So tangent of theta, so that is from here. Tangent of theta is equal to x over square root of 1 minus x squared. Okay, I hope this discussion was useful in helping you understand what's happening in terms of when we have an inverse of a trigonometric function and we want to calculate quantities based on that. So this wraps up our discussion of section 6.4, and thank you for watching this video, and have a nice day, and I'll see you all next time.